In the last video, we looked at the volume of common objects, and volume is really important for things like weight, anything that deals with the bulk object. Now, surface area is really important on anything that relates to the interaction between one object and its surroundings. So the flux of something, right? So if you're heating an object and you know the flux, then the surface area is going to tell you how much of that heat is going to be applied to it. You can think about this from a force perspective, anything that there's an interaction between an object and its surroundings. Surface area is generally an important factor. So let's take a look at some common shapes and see how we can determine what the surface area is. So the first shape that we looked at in the last video was the cylinder, and we were able to determine the volume by knowing the area and multiplying that by the length. If we want to find the surface area, we need to first identify what surface we're actually solving for. Sometimes the surface area that you're interested in is just this outer surface. Sometimes you also care about this top layer and the circle at the bottom layer. So it really depends on what surface you're looking for. If you're just looking at the top or bottom layer, then it's just 2 times the area of the circle. So 2 pi r squared, right? If you're also interested in this side component here, that will just be the height L times their circumference right here. So their circumference 2 pi r times the length L. An easy way to think about this is if you get a piece of paper and you roll it into a tube, right? When you unravel it, it's basically a rectangle. So you multiply the length of it by the width of it. In which case, if you unravel this, that's just this length here, the circumference here, would be the width of that rectangle when you unravel it. Let's take a look now at a rectangular prism. We use the area and the volume, and the length to determine the volume of this. If you want to solve for the surface area, you need to recognize how many surfaces you have. You have this surface, replicate it on the back end here. You have this top surface, replicate it on the bottom surface here, and you have this right surface, replicate it on the left surface here. So if you're interested in all surfaces, then you would need to add all 6 surfaces together, or recognizing that the front and back are the same, top and bottom are the same, and the right and left are the same, you could say 2 times and add those 3 surfaces. And these are just rectangles. So you would have h times w for this front and back surface, w times L for the bottom and top surface, and the height times the length for this right and left surface. Now we can even be more specific if we have a cube. If we have a cube, this would be, so we know the volume of the cube, L cubed, or L, the length cubed, right? If we want to solve for the surface area of this cube, and we care about all surfaces, we can count how many surfaces we have. You would count 6, right? You see 3 here, and then you have the back one, number 4, the left one, number 5, and the bottom surface, this number 6. All, because it's a cube, have the same area, front-facing area. So it will be L squared is the area times 6. So 6 times L squared. Okay, and finally, we have our triangular rectangular prism, or triangular prism. We determine the area, we use the area of a triangle, this front-facing triangle, and we extrude it to solve for the volume. And we said 1/2 the height, assuming this height is the perpendicular length here, times this base, right, for the area of this triangle, times the length L. Now, if we want to find the surface area, we should first identify how many surfaces we have. We have this triangle up in the front, a triangle in the back, a rectangle on the left, a rectangle on the right, and then this bottom surface here. So you need to account for each of these. So we can count for here, right? So we got the base times the length, base times length, that's the bottom surface, plus 2 times 1/2 the base times height. 1/2 base times height is the area of the triangle, right? And we have two of them, with one in the front and one in the back. And so the last thing we need is this rectangle right on the left and right. So this will be 2 times, because we're saying for this specific example, it's the same on this side and it is on this side. And we can just look at the rectangle, right? So we have a length L, and then this length here we don't yet know, but we can use Pythagorean theorem. We say, all right, if I draw a right triangle here, right, splitting this isosceles triangle in half, we have a base that's 1/2 the base, and the height is h that we're given. So we can use Pythagorean theorem, where we'll say square root of the height squared plus the square of the quantity 1/2 the base would equal to this length here. And that's what we have here. So we can see that we can find the surface areas of these extruded objects fairly easily. Now it's important to look at a problem statement, actual engineering physical problem, when it asks for a surface area for a physical property, which surfaces you actually are trying to account for. So a lot of times when we're looking at like a pipe, you wouldn't account for the inlet and exit components. There might not even be any area there. You might be only interested in the length surface area because you have something heating a pipe or cooling a pipe. If you're looking at a cube, you might be only interested in one surface that's exposed to a fluid flowing over it, and the bottom components are just structural, and you would be interested in the shear components, right? So just because we say surface area of a specific object doesn't mean it's going to be what we have here. You might remove certain terms because you're only interested in the specific surface of the entire volume. All right, so let's take a look at 2 more objects and solve for the surface area of those. So we have our sphere here. We were able to derive the volume of those spheres through integration. But now if we want to find the surface area of the sphere, we're going to find that it's equal to 4 pi r squared. So where does this even come from? There's 2 ways we can approach this. One way to notice is think about a very, very small sphere at the center of this larger sphere, and think about defining the surface area of that sphere. Then take a incrementally small step in the radial direction and have a slightly larger sphere, right? So the center still being at the center of this larger sphere, but it's a slightly larger radius, and calculate the surface area there. And keep doing that until you reach a radius of little r. If you add all those surface areas up, you basically have the entire the larger sphere, and that would be the volume of the sphere. So that tells us that if I integrate this surface area with respect to a changing radius, dr, little r, then I would get my volume. So that means that I also can take the derivative of the volume with respect to r, and then I can get my surface area. So if we do that, take the derivative of volume with respect to the radius, I get 4/3 pi r cubed. Take the derivative of that, that's the volume, with respect to r. 4/3 pi is constant, so I can pull that out. The derivative of r cubed is 3r squared, and so that gives me my 4 pi r squared surface area. Now another way we can do this is by integration. What would I integrate for my surface area? So instead of integrating the area of a disk like I did for the volume, I would integrate the edge surface area component here. Okay, so it will be a incrementally small surface area that's defined by the circumference of this disk multiplied by whatever this height is. So how would I define that? Well, the circumference of this disk is 2 pi cap r. Capital R is defined in terms of theta, and little r. Little r is a constant. That's the full radius of the sphere. So cosine theta, where theta is defined as from this 0 x-axis component as positive in this direction. So this will go from 0 to pi over 2 and from 0 to negative pi over 2 down here. So those are the limits I'm taking, right? So that will take my disk from up here all the way down here. So that's how these limits are applied. So 2 pi r is the circumference of this disk times that height right there is a r d theta. It's a arc length component defined by your theta term. All right. So then I can replace capital R with r cosine theta. That's what we have right here. And I can solve this integral. So 2 pi r squared are constants. So then we just multiply that by the integral of cosine theta. Integral of cosine theta d theta is just sine theta. And then we apply the limits pi over 2 and negative pi over 2. Right? At pi over 2, sine theta is what? That's the y component. So that'll be positive 1. At sine negative pi over 2, that'll be the y component in the negative y-axis direction. So that'll be negative 1. So 2 pi r squared times 1 minus negative 1, or 4 pi r squared. So we get the same solution there. So for our last object, we're going to take a look at our cone. So remember, we calculated the volume of the cone, and we were able to generalize this to other pyramids by saying 1/3 because of the triangular shape times pi r squared because of the base area times height was our volume. If I'm interested in surface area, we see that we have two surfaces: the surface that's wrapped around for the top of the cone and the bottom circular area right here. So we can define the surface area for this entire object. And what we'll find is this is pi r squared for this bottom component here, and up here is going to be pi r times square root r squared plus h squared, where square root r squared plus h squared is just this length right here, right? Sometimes you might see it defined as like a capital L, like some type length component. But the question is, why is it pi r times that length, right? So you can create a cone, you can unwrap it, you can see that it's not going to be the circumference multiplied. This is exactly 1/2 of that. So where does this come from? So we'll show a derivation similar to how we derive the surface area for the sphere, but specifically for this section right here. And we'll call this section AS2. And so we're going to look at it from a very similar perspective as we do here. Let's define the point starting up here to where I'm looking at my disk as a little l. Capital L, right, the full length here is, we're just going to describe it as square root r squared plus h squared, right? So using Pythagorean theorem, and we draw a triangle right here. This length, this full length here, is the radius squared plus height squared. So if I look at my disk here, and I'm interested in that thickness surface area, I can multiply the circumference, 2 pi capital R, times that incremental length dl, right? So we're looking at this dl in the same direction as this L component right here. And capital R, we want to find a relationship with that and little r and L, the length up here from the top point to the disk. And we see that we have similar triangles. So this triangle and this larger triangle have similar relationships. So the ratio of values has got to be the same. So you can think about it as the R component related to the length component, or this L component, has got to be the same as this larger R component, right? Which I guess counterintuitively defined as little r, and the total length component, right? That total length component is square root h squared plus r squared. So I can say R, capital R divided by little r is the same as the length L over the large L, square root h squared plus r squared, right? So I can replace this relationship to this r value right here. And so that's what I do right here, right? R L over square root h squared plus r squared. Okay, so what's constant? 2 pi r is constant. Square root h squared plus r squared is constant. The only variable term is my length, my little length L right here. And I'm integrating from 0 to square root r squared plus h squared. What does that represent? The 0 represents this point up here. The full length is represented by square root h squared plus r squared plus h squared, right? The full length here. So we're starting from here until the length L becomes that full length. So that's the integration. So I can pull out my constants, 2 pi r over h squared plus square root h squared plus r squared. That's this term right here. So the only thing I'm integrating is L dl. So L dl, the integration of that is just going to be L squared over 2, right? That's the same thing as integrating x dx. And I apply my limits. This term squared minus 0, so it's just this term squared, right? This term squared. That cancels out with this denominator term right here. So we get pi r square root 8r squared plus h squared. That's exactly what this section is representing. So again, for this cone, it depends. Most likely, you're most interested in the surface area defined here, and not so much that base surface area. But it really depends on what your system is looking at. You can look at other area terms within these volume components, like section components or cross-sectional areas. Sometimes some of these surface areas are defined as cross-sectional areas. It really depends on the context that we are looking at. So now that we have volume and surface areas defined, the next set of videos we can look at, what if I vary a certain parameter? How does that vary the volume or surface area of one of these objects? Now that becomes very important once you understand what properties are altered by the volume or surface area. Then you can define, if I change one of these variables, most of the time it's not a linear relationship. And so understanding what that relationship is can help you define and design things from an engineering perspective for performance. So we'll look at those in the next set of videos.